Welcome to another physics class. During our last lesson, we're done with motion under gravity. And please, if you are just joining us on this channel, don't forget to like, share, and subscribe so that when I have a new video like this, you'll be able to get the notification in time. So today, our topic is projectile motion. Projectile motion is a plane parabolic curve of an object thrown vertically upward into space, which varies with time and be influenced by acceleration due to gravity. I take it again. Projectile motion, a plane parabolic curve of an object which thrown vertically into space and vary with time. At the same time, the motion is being affected by acceleration due to gravity. Let's try projectile motion. Projectile motion is a plane parabolic curve of an object which is vertically thrown upward and varies with time. That is, motion of an object, parabolic curve, thrown vertically upward and vary with time. When you say motion is parabolic curve, that is something like this, or let's say this is wall, something like this. So this is parabolic in nature. So when you have motion of an object, follow this pattern. Then such motion, we call it projectile motion. Or for instance, in another way, when a tennis ball kick against the wall and bounce back, the curve will be like this. So the curve like this shows parabolic curve. And this type of an object that is performing this one, that object is a projectile. And the motion performed is projectile motion. Now, let's look at examples of projectile motion. Examples of projectile motion. One, a bullet shot from gun. A bullet shot from gun. As I explained the other time, when a bullet is released or shot from gun, the motion of the bullet will look like this until it come back to the ground. Something like this, something like this. So the bullet will move like this. That's a typical example of projectile motion. Number two, an arrow shot from bow. An arrow shot from bow. I think when you shot an arrow from bow, it's another example of projectile motion. Let's say this is a bow, this is an arrow. When it's being released, then the motion will move like this and curve like this when it's about to land. That's another examples of projectile motion. In short, any projectile that performing projectile motion, that is perform a parabolic curve. Number 3, a stone released from catapult. A stone released from catapult. When a stone is also released from catapult, the curve will also form a parabolic curve. Number 4, a thrown javelin. When a javelin is being thrown, it forms a parabolic curve. Number 5, a thrown shot put. Shot put is a sport material. When it's being thrown, it must follow a parabolic curve. Number 6, a thrown discus. Discus is another sport material. When it's being thrown, the motion must follow a parabolic curve. There is reason for underline all those ones. Number 7, an athlete. Diving. An athlete diving. Long jump. An athlete diving, long jump, or high jump. An athlete diving, high jump. Then number 8, a missile bomb released from airplane. Missile bomb released from airplane, the motion also is a parabolic curve. Number 9, a landing airplane. When a plane is about to land, the motion will form a parabolic curve. Number 10 example, a kick football. When a football is being kicked, the motion will form a parabolic curve. Number 11, a tennis ball. Kick again the wall and bounce back. The tennis ball kick against the wall and bounce back. As I said the other time, when you throw a tennis ball against the wall and bounce back, the motion will curve like this. So that's a typical example of projectile motion. Let me add one more. Number 12, a table tennis ball played. A table tennis ball played. When a table tennis ball is being played, the motion is form a parabolic curve. So all these are possible examples of projectile motion. But note the underlying word. All these underlying words, we are still coming to this. Next is projectile itself. We need to know what meant by projectile. And when you say projectile, it is that particular object launched into air or space that perform projectile motion. That is that particular object itself that launched into space in order to perform projectile motion. And from the underlying word, in this example now, for instance now, when you take the first example, a bullet shot from the gun, the projectile there is bullet. Look at example 2, an arrow shot from bow. The projectile there is arrow. Dictate to example 3. So in short, all these underlying words, underlying items are typical examples of projectile. That is that particular object that launches into space to perform projectile motion is what is meant by projectile. Let's write projectile is an object launched to space, launched into space to perform projectile motion. That is an object launched into space to perform projectile motion. Or in short, you can define projectile motion as that particular object that the motion is parabolic curve in space. That is, the motion of that particular object will be parabolic curve in space, and it will vary with time. Examples of projectile as listed, underlined under this example. We can have bullets, arrow, and javelin, shot put, discus, missile bomb, stone, airplane, and tennis, any kind of ball, either football or you say tennis ball, any kind of ball, or cricket ball, or cricket ball. So any kind of ball can be used to perform projectile motion. Now, from the list of these examples now of projectile, you cannot say that when you have to state examples of projectile motion, you state it like this. This is examples of projectile motion. That particular object that is performing that projectile motion, you need to mention it in your statement. That is a bullet shot from gun. But on the other hand, when you have to mention examples of projectile, so these are what you need to mention: bullet, arrow, javelin, shot put, discus. So it's different from examples of projectile motion. When it is examples of projectile, that particular object itself is what you are going to mention. Next is application of projectile. Application of projectile. Projectile are applicable in the following area. 1. In sport. That's number 1. Then, from the list of the projectile on the board, what are the projectile that can be applicable in sport? Example now, you can answer examples of projectile in sport. We have, according to the list, tennis ball, football, cricket ball, that is the one that we can use in sport, discus, shot put. All these mentioned projectile are used in sport. Number 2 application is it is applicable in warfare. Projectile also is applicable in warfare. Then, what are the possible examples of projectile that we can use in warfare? Examples of projectile in warfare. That is, those projectiles that can be used as weapon. From the list on the board, we have stone, arrow, missile bomb, or any kind of bomb. So these are the 3 that we can use in warfare. In addition, we can still have bullets. Any kind of bullet can be used in warfare. And number 3, it is also applicable in flight. It's also applicable in flight. What are the possible examples of projectile in flight? Examples of projectile in flight. These are airplane, rocket, jet, then kites, etc. So these are the possible examples that we can use in flight: airplane, rocket, jet, and kite. Next is what we call trajectory. When you say trajectory, it simply means the path or the direction of a projectile. That is, trajectory is the path followed or direction of a projectile, the path follow or direction of a projectile is what we meant by trajectory. I think when you say trajectory, the path followed by a projectile or the direction followed. For instance, when a tennis ball is being played, a tennis ball playing, the curve is like this, from one player to another. The curve is follow. So this path followed by the tennis ball is what we call trajectory. Or when you kick a tennis ball against the wall and it bounces back, this is the wall now. Wall. You kick it against the wall and it bounces back like this. This is what meant by trajectory. That is the path follow or the direction of a projectile is what meant by trajectory. Or if it is a stone released from catapult, so the stone will travel like this, move into the air and come back to the horizontal. So the path followed by any projectile is what we meant by trajectory. So it will hit the, so this is what we meant by trajectory. Is terms used in projectile motion. Terms used in projectile motion. The first one, number one, is time to reach the maximum height. This one is denoted by small t. And we say time to reach the maximum height is the time taken by a projectile from point of projection to the maximum height. I take it again. Time to reach the maximum height is the time taken by a projectile from point of projection to maximum height. That is when you project or you launch a projectile into space or air like this. Let's say this is the maximum height from this is the point of projection. The time taken to reach this maximum height is what meant by time to reach the maximum height. This is the time taken from here to here is the time to reach the maximum height. Let's write it down. That is the time taken by a projectile from point of projection to reach the maximum height. The time taken by projectile from point of projection to reach the maximum height. Let's say this is the horizontal level where the projectile belongs to the air, and this is the maximum height it reached before it returns to the ground. So from here to here, the time taken from here to cover from this place to this place is what meant by time to reach the maximum height. Number two, time of flight, capital T. The time of flight of a projectile is the total time taken by that projectile from point of projection to return to the projection plane. That is, the time of flight is the total time taken by projectile from point of projection to where it returns to the projection plane again. So from time taken to cover this plane to this projection plane now, this is point of projection. So the time taken to cover to this plane is what meant by time of flight. So let's write it. Is the total time taken by a projectile from point of projection to where it hits the projection plane. Again, that is time used to cover from here to here. That's time of flight. This is maximum height. This one, when you say maximum height, as I explained the other time, let's say this is the plane of projection. Then when you launch a projectile into here like this, it reaches the maximum and come back. So from here to here is the maximum height. That is, when you say maximum height now, is the vertical displacement raised by a projectile. The vertical displacement, or the maximum vertical displacement attained by a projectile is what meant by maximum height. Let's write it. Is the maximum vertical displacement raised by a projectile. That is the maximum height. Is horizontal range. That's number 4 terms. Number 4, horizontal range. When you say horizontal range, we talk about vertical distance the other time. This one is the horizontal distance. That is, this point of projection, this is where it hits the projection plane again as it travels like this. So as it travels like this, this is where it hits the projection plane again. Now, when we now say horizontal range, this one denoted by capital R. Now, is the horizontal distance covered by a projectile from point of projection to where it hits the projection plane again. That is, this horizontal distance from here to here is what we call horizontal range. So, is the horizontal distance covered by a projectile from point of projection to where it hits the projection plane again. That is from here, this is projection point of projection. This is projection plane. So when it travel, the horizontal distance covered. So from here to here now is the horizontal distance. These are the major terms used in projectile motion. The next we are going to look at is projectile motion equation. As we did under linear motion, so also under motion under gravity, we are going to have equation for all those terms that we have defined. That's it, the time to reach the maximum height, time of flight, maximum height, and the horizontal range. When you say projectile motion, note this. Projectile motion is a two-dimensional motion. Projectile motion is a two-dimensional motion. One, we have horizontal constant accelerated motion. In this case, the motion of a projectile horizontally is usually constant. Why is this constant? Because when projectile is moving horizontally, there is no horizontal acceleration. So under this one, acceleration due to gravity, G, is equal to 0. So the fact that G is equal to 0, that is why the horizontal motion of a projectile is constant. So that is, as I drawn the other time, how the object is moving like this, it will cover a horizontal distance. It will cover horizontal distance. And under this horizontal distance, the acceleration is constant. And once the horizontal in the horizontal distance, G is constant, then G is equal to, acceleration is due to gravity is constant, so G is equal to 0. And the fact that G is equal to 0, that is why the horizontal distance of a projectile is always constant. Number 2, vertically accelerated motion. That is, when it is being launched into here, two things will occur. It will move vertically like this, moving vertically like this, at the same time moving in horizontal direction, moving vertically like this. So for the second one now, vertically accelerated motion, then the acceleration due to gravity under this one is not equal to 0. That is, when you say vertically accelerated motion, it means acceleration due to gravity have effect on that motion. So the first one, horizontal constant accelerated motion, G is equal to 0 because there is no horizontal acceleration. And as I said, that is why the motion of an object under this projectile motion moving horizontally is always constant. The second one, vertically accelerated, by the time you throw it up, it will move vertical. And when it moves vertically, then the acceleration due to gravity have effect on that one. So the second one, acceleration due to gravity have effect. Let's consider a projectile launched into the air like this. We want to use this one to derive the equation of projectile motion. A projectile launched into air like this. From what is drawn on the board now, U is equal to initial velocity. of the projectile. Theta here is equal to angle of projection. Uy is equal to initial particle component velocity. Us is equal to initial horizontal component velocity. And when R is range or horizontal range. H is maximum height. So having considered all this for now, U is initial velocity as has been written on the board, dictate to all other notation. Now from this diagram now, if you look at it like this, we use this one to form a right angle like this now. Let's say this is Uy, this is angle theta. We want to use vector method now. And this is Us. Now, let's first use it like this. Like this, our Uy can also be here because this line is equal to this line. If you take it like that, now let's resolve it vertically. Resolve vertically. If you resolve this one from this vertically, then it means we need to close this one. This is the line for U now. We need to close this one. This is vertical line, or this one. So if you resolve this one vertically, our Uy can be here. So our Uy can be also here because the lines are equal. So if you resolve it vertically, then you need to close Us. Vertically, it will remain this one, and this one. And if you look at it, this one will be opposite, while this one will be hypotenuse. Doing it like that, that one will be sine theta. That is from mathematics, opposite over hypotenuse. That will be Uy over U. So it means our Uy now will be equal to U sine theta. Note this formula. And don't forget the interpretation of the Uy from this one. That is initial particle component velocity. That is the magnitude of the initial particle component velocity of any projectile is Uy is equal to U sine theta. At the same time, if you now resolve horizontally, if we resolve horizontally, that means we close this side. The vertical axis will be closed. It will remain the Us, U, and theta. Now, if you consider this one now, this one will be to this angle. This one will be adjacent, while this may will be what? Hypotenuse. And that will be cos theta. Cos theta now will be equal to Us over U. Therefore, the Us now will be equal to U cos theta. Don't forget, our Us also is what? Initial horizontal component velocity. initial horizontal component velocity. Now, for US, note this formula also. So when we get to calculation, we are going to apply it. So we've seen two now. The first one, initial vertical component velocity, and the second one, initial horizontal component velocity. Let's now move on to time to reach the maximum height. Time, according to the definition, we define the other time to reach maximum height. That is small t. Now, under this one, this is where we are going to combine linear equation together with motion under gravity, and we are going to use the two to find or derive the equation for each term that we define in projectile motion. Now, for linear motion, or let's quickly go to motion under gravity, we said V is equal to U plus or minus GT. Don't forget, if you are not just joining us, we've done with this one under motion under gravity. So therefore, try to like, subscribe, and so that you'll be able to get the topic on this topic, that is motion under gravity, and you connect it with this one. The second one, H is equal to UT plus or minus half GT squared. V squared is equal to U squared plus or minus 2GH. Don't forget, we've done lengthily on these three equations when we are dealing with motion under gravity. But now, to derive time to reach the maximum height now, we are going to apply equation 1, which is V is equal to U minus GT, because we say it's time to reach the maximum height. Since this one is from motion under gravity, we need to relate it to what we are doing, projectile motion. So under projectile motion, we are going to have Vy minus U are equal to Uy minus GT. Mind you, it's time to reach the maximum height. That is why we say component. When what we call component here is the X and Y axis. We call this one initial vertical component velocity. And this one will be final vertical component velocity, that is Vy. So, but don't forget what we have done again under motion under gravity, that at maximum height, Vy will be equal to 0. Don't forget. If Vy is equal to 0, then we are going to have is 0 is equal to Uy minus GT. The time to reach the maximum we are looking at is this t. So let's make it as the subject of, so therefore G now is equal to Uy, T is equal to Uy over G. Uy over G. And don't forget, what is our Uy here? And now say, but Uy is equal to U sine theta. Therefore, the time to reach the maximum height will be equal to U sine theta over G. That is time to reach the maximum height. And mind you, when you are now dealing with projectile motion and motion under gravity, the only difference between the two is if it is motion under gravity, no angle will be given. If you can look at the calculation under motion under gravity, no angle was given, no angle was how to calculate. But here now, angle is involved. The angle that's involved now will now tell us the question given to you is under projectile. But if angle is not given, and the question just say a ball is projected vertically upward, and angle is not given, don't forget that's motion under gravity. Now the angle is involved. So T now is equal to u sine theta for time to reach the maximum height. And if you can still remember what we did under motion under gravity, time to reach maximum under motion under gravity is equal to T is equal to u over g, if you can still remember. Here angle is involved, so we are T is equal to u sine theta over g. Now the next one is time of flight. Time of flight. Time of flight. Don't forget again, when we are dealing in motion under gravity, I said when you have the motion starting from the same horizontal level and land on the same horizontal plane like this, I said the time of flight will be equal to T, capital T is equal to 2T. If that is the case now, and our T here is u sine theta over g, so we can now say T now is equal to 2u sine theta over g. That's time of flight under projectile. Now, the number 3 terms we mentioned is maximum height. We want to derive equation for maximum height as we read to time to reach the maximum height and time of flight. Now to do this one also, don't forget our 3 equations. We are going to apply equation 3 now. V squared is equal to u squared maximum height, that will be minus 2gh. Now, this is formula under motion under gravity. Let's now relate it to projectile motion now. It will be Vy squared is equal to Uy squared minus 2gh. That's what makes the difference. Now, we said at maximum height, Vy will be equal to 0. At the same time, also, Uy, according to what we've done the other time, is u sine theta. So if that is the case, we now give us 0 will be equal to u sine theta all into square minus 2gh. Don't forget, what are we looking for? Height. So let's make the height of the circle. So 0 will go away. Then we are going to have 2gh is equal to u square sine square theta. What do we need? H. So we are going to have H will be equal to u square sine square theta over 2g. That is for maximum height. Now, don't forget, the question may ask you, written this all this formula and ask you to define its notation. So from here now, our where h is equal to maximum height, u is equal to initial velocity, theta is equal to angle of projection, and g is equal to acceleration due to gravity. I say acceleration due to gravity, not gravity. Now, in another way, they can still ask you in another question that the maximum height of a projectile depends on what factors? The factor also remain the same. 1. Initial velocity of the projectile. 2. Angle of projection. 3. Acceleration due to gravity. That's another question. In a question, it can be written like this and ask you to interpret or define its notation. We define its notation. In another question, you may be asked that the factor that determine the magnitude of maximum height of a projectile are, so these are what I've mentioned. What is inside the formula are initial velocity, angle of projection, and acceleration due to gravity. Those are the factors that determine the magnitude of maximum height of a projectile. Let's move further from this one now. For h to be maximum, for h, or for h, that is the height, for height to be maximum, for height to be maximum, the value of theta, that is value of theta, that is angle of projection, must equal to 90 degrees. That is, when you throw an object vertically upward like this, as it's moving up, the angle will be increasing. When it reaches 90 degrees, then the maximum height will be attained. At that particular angle, when theta is 90 degrees, then we are going to have maximum height. So from there now, if theta is 90 degrees now, sine 90 will give us 1. Therefore, we can now say sine 90 will be equal to 1. So we are going to have h maximum when u as u square over 2g. When theta is 90 degrees. That is, when theta is equal to 90 degrees, we are going to have h maximum. Now, the last term that we need to derive equation for is horizontal range. And don't forget, for the diagram we drawn the other time, when you have it like this, so this angle theta from here to here is our horizontal range, which is r. Now, if that is the case now, and again, don't forget again, we borrowed these formulas from motion under gravity. We use the first one for time to reach the maximum height, the second one for maximum height. So let's use this third one for horizontal range now by saying h is equal to ut plus, because it's horizontal, half gt squared. Now, this is what we borrow from motion under gravity. Let's now relate it to projectile motion now. If it is, we said horizontal range, not vertical height. So this our h, we change to r. Because we say horizontal range, that's why we define horizontal range as horizontal distance. Now, for this, our ut, our u here, horizontal range. Now, our u now will now be equal to us, because it is horizontal, not ordinary u. Mind you, we borrowed the formula from motion under gravity. Then our t now, this t, since it is horizontal range, and when you say horizontal range, that should be time to cover from here to here. So our small t will now be capital T. That is time of flight from here to here. This is borrowed formula. We are now translating it to projectile motion. And this is how to interpret it. H will change to R. Our U will be US. T will be capital T. Because if you consider this thing now, under motion under gravity, this thing will be time to fall from maximum height to the ground. And we need total time taken now. Now, again, our G, which is acceleration due to gravity, will be equal to what? According to the first explanation, that projectile motion have two-dimensional equation, dimensional motion. One, horizontal constant motion, in which G is equal to 0. Here now, G will be equal to 0 because it is horizontal. So if G is equal to 0 now, it means this term will be equal to 0. And what we are left with will be H is equal to UT. Comply with what I've written on the board. Our R now will be equal to US capital T. And don't forget again, in the beginning, we've said US is what? Initial horizontal component velocity. Can now say but US is equal to U cos theta. And again, this our T is what? Time to reach the time of flight. So at the same time, also, our capital T is equal to 2U sine theta over G. Written the two together now, our R now will be equal to U cos theta into bracket 2U sine theta over G. So when we write the two together, now from here now, we are going to have, open the bracket, U squared 2 sine theta cos theta over G. And if that is the case,